After computing a couple of example problems using Biot-Savart's law, you might be wondering if there is an analogy in magnetic fields to Gauss's law. So if you remember, in Gauss's law, we found that we could compute the electric field much easier than using Coulomb's law. Coulomb's law involved a lot of integrals and vectors and curly r hats, and it was kind of a mess. But Gauss's law allowed us to calculate the electric field rather simply. For instance, if we had a cylinder that was filled with some uniform charge density rho, we could calculate the electric field inside the cylinder using Gauss's law relatively straightforwardly. And this was really quite nice. And we found that Gauss's law was always true, but it's not always useful. In particular, it's only useful in cases that have high degrees of symmetry. So is there something similar for magnetic fields? And yes, there absolutely is. So let's imagine that we have, instead of a volume of charge, we have a volume current, J, flowing in the z direction here. And this is a thick wire with a radius r0, so almost the analogous magnetic version of this situation. And we could ask, what is the magnetic field inside the thick wire? That might be a question we might be interested in knowing. Calculating this using Biot-Savart's law is really ugly and really not a nice calculation. But using something called Ampere's law, we can calculate it relatively easily. So Ampere's law looks a little bit different and a little bit similar to Gauss's law. So Ampere's law says that if you take the line integral around a closed loop of the magnetic field dotted with dl, the little bit of length around that loop, that line integral is equal to that constant mu naught times the current enclosed by that loop. You can notice some similarities with Gauss's law. The Ampere's law has a closed loop instead of a closed surface, but otherwise it looks very similar. There's a similar dot product on the left-hand side, and then something about enclosed current on the right-hand side, whereas in Gauss's law it was enclosed charge. Just like Gauss's law, Ampere's law is always true, and it's only useful in cases that have high degrees of symmetry. Let's just look at one simple example to apply Ampere's law to get started. So let's consider a just long straight wire, infinitely long wire, and we want to know what is the magnetic field around this wire. Now, we already know the magnetic field around this wire. We've computed it using Biot-Savart's law, but let's try and use Ampere's law to see how Ampere's law works. So in order to apply Ampere's law, we follow a similar strategy as what we did for Gauss's law with electric fields. So first, let's use some symmetry to write a form for the magnetic field, B. Oftentimes, you're going to use the right-hand rule to figure this out. If I use the right-hand rule on this wire, then my hand curls around the wire in the direction of the phi direction by cylindrical coordinates. And by symmetry, I know the magnetic field can only depend on the distance from the wire, s. And so using those two pieces of information, I'm going to use that symmetry argument to say that the magnetic field B is B of s, so it's only a function of s, the distance from the wire, and it points in the phi hat direction. Next, what we do for Ampere's law is we have to choose an imaginary Amperian loop that matches the symmetry of our problem. This is similar to when we chose an imaginary Gaussian surface before. So because our magnetic field is curling around in the phi direction, I'm going to choose my loop to also be curling around in the phi direction. So I'm going to choose an Amperian loop that curls around like this, and I'm going to give it some radius s. Notice that I'm giving it a radius that is a coordinate, just similar to what we did in Gauss's law, so that way it's an arbitrary radius for this loop, and I can figure out the magnetic field at any distance from the wire. Now that I've chosen the imaginary Amperian loop, I'm going to evaluate the integral of b.dl on that loop. So that means I need to figure out what dl is. So dl on this loop is s d phi phi hat. So s d phi is the little bit of length, and then it points in the phi hat direction. Notice that that dl inside the line integral has a direction on it. But as with Gauss's law, I mean, it looks like we're doing a dot product, and it looks like we're doing something here, but really we're going to turn this into an integral that we don't actually really have to think much about. So in particular, we plug in our symmetry form for B, that's B of s phi hat, and we dot that with s d phi phi hat. Well, I only need to worry about the dot product here between phi hat and phi hat, which gives me 1. The s and the b of s don't depend on phi. Those are just constants from the perspective of the integral, and so they can just come out of the integral. And so I have s b of s times the integral from 0 to 2 pi of d phi. Oh, that's just 2 pi. So this line integral, I didn't really even have to do a line integral. I just turned this line integral into the circumference, 2 pi s times b of s. That's maybe another way of looking at this problem. The next step in Ampere's law is to evaluate the current enclosed, I enclosed, for this loop. So the idea here is how much current actually goes through the loop we've drawn. Sometimes it helps to shade the loop to see how much current is actually going through that loop. And so in this case, there really isn't any ambiguity. The current enclosed is just the total current, I. In other cases, like for a thick wire, we'll have to think a little bit more carefully about this. But in this case, we just get I for the current enclosed. Well, we've got the left-hand side of Ampere's law. We've done the line integral. We've got the right-hand side. We've got I enclosed. We just need to set them equal to each other with that factor of mu naught. So I have 2 pi s b of s is equal to mu naught times I. And I need to solve for the magnetic field B. So the magnetic field B as a function of s is mu naught over 2 pi I over s, where s is the distance from the wire. This shouldn't be much of a surprise. This is what we found from Biot-Savart, but that involved cross products and doing an integral that was nasty. We didn't really have to do much at all. We just had to use the symmetry of the problem in order to use Ampere's law. So that's the advantages of using Ampere's law, similar to Gauss's law.